Hello guys, welcome back to my YouTube channel. In this video, we will see what exactly is the data warehouse and why most of the companies can't run without having a data warehouse. So in this video or by the end of this video, we will go through all these concepts. First, we'll understand the main problem of like why production database breaks for analytical queries and what is the multi-source data problem and what is the real historic problem and why did he come up with the data warehouse, and then we will dig deeper into what exactly is the data warehouse. Here we'll be discussing about OLTP versus OLAP and its differences and everything, and the difference between the row based storage and the column based storage. And then we will be coming to the concept, why most of the companies use columnar storage, why most of the DBs are actually columnar storage, and why exactly these columnar storage make the analytics queries very fast. And then we will come to understand how exactly it works. For that, first we need to understand the difference between ETL and the ELT, and then we'll go dig deeper into the three warehouse layers, from raw to staging to Marts. Then we will understand the full architecture. For example, like data coming from the source, it will go through the pipeline, and data will be stored into the warehouse. From there, business intelligence, it will directly hit the dashboard, and from there, business persons can view the dashboard. Next, we will take an example of the BigQuery, and we'll just dig deeper into the specifications of the BigQuery, like how exactly BigQuery stores the data. Here, we'll go dig deeper into the architecture part of the BigQuery. Like we'll be discussing about the terms like capacitor, coalescence, architecture, and everything, and then we will see the difference between compute and the storage sessions, and exactly we'll see why exactly it's called a serverless, the main thing. And also we will discuss about the BigQuery related and partition pruning, and also about the clustering and how it helps to reduce the cost. And then we will discuss some of few of the common mistakes which we usually do and we could able to notice by ourselves. Okay, now we'll discuss the main problem, and the first thing is why production DBs aren't enough, or why we are using the data warehouses. See, this is how what the production DBs are built for. Just imagine there is a user and user places an order. It will barely take 2 milliseconds to update a single row. Same way, if the user logins, it will just update in single row with saying like the user has login. These kind of similar operations usually take milliseconds to perform these operations. So the writing will be the very fast here in this case. So this is what the exact production DBs are usually built for. Now just imagine the manager or the business intelligence person comes and asks, revenue by product category every month last 2 years. Now for this, if we are using this production DBs, we will be literally scanning the last 2 years of data. It might be 50 million rows or many. And after scanning these 50 million rows, we will need to use some mathematical operations like grouping by, every month, or doing some sum operations, sorting operations, everything. So literally one query will take more than 1,000 seconds for each and every user request if the user asks this kind of request. So this will be heavy load in the production database. That the reason is, see, these kind of operations are everything going in the same production DB, and these kind of operations are also going into the same DB. It's like single machine and multiple requests coming up, and the multiple requests also have this kind of heavy up queries. So just take an example here. See here I have mentioned like OLTP versus analytics. For now, just imagine this is like only transactional processing and analytical processing. Here is nothing but this kind of operations, and analytical processing is these kind of operations. Now just imagine if you see OLTP, like this kind of operations and everything, it is barely one row entering and one row out. This is what exactly it does, updating a row or adding a new row or deleting a new row or something like that. It barely touches one single row here, and the speed is obviously in very milliseconds. Now if you take such kind of analytics query, which is like when the manager or the customer asks these kind of questions, now we need to scan like n number of rows. It might go to million rows, and we need to aggregate and do such kind of operations. This is what exactly the analytical queries does, and it will barely touch, we are not sure of the exact number, it might scan the whole table in some cases, and the speed will obviously take to the minutes, not in the milliseconds. So the only possible solution if we have this kind of situation is we need to either stop running these queries in the daytime, and we need to only run it like somewhere around morning 2 a.m., where users perform these kind of operations very less. So it's like either this or this. So This kind of problem is exactly called the noisy neighbor problem. So this is what we call it as a noisy neighbor problem. So this is not best way of scaling in the long term. So this is one of the main problem why production DBs are not enough. Okay, now second problem is the multi-source problem. So the concept is simple here. So usually data lives in silos. Silos is nothing but, I'll just show you an example of what exactly silos is. Silos is nothing but, I just took an example of this big tankers, which we store in the industries. So the whole concept here is, see, so data is usually stored in the different places. See, app orders is stored in one place, Stripe payments is stored in Stripe website, and these kind of tickets are stored in Zendesk, and Google related ads and everything stored in the Google ads, and maybe some other data is stored in the spreadsheets. So now just imagine the customer comes up, asks this kind of query: who bought the product X and opened a support ticket within last 30 days? Now we have the product details here, all this in the app orders, and we have the support tickets and everything details and everything in the support gen desk tickets. Now the question is, these are not linked, this is in some other, this is coming from the some source, everything is totally independent. If you see this table, so we have the source of app DB, this knows about the orders, but it doesn't have any idea about the tickets and the ads. And this has the Stripe DB, it has only idea about the payments and don't have idea about the product and the ticket details. Same go for Zendesk tickets. So it knows about the tickets and everything, but it doesn't have a single idea about the revenue and the ads. So this is the problem with the multi-source DBs. Now see, now just imagine everything is stored in the data warehouse. So in the data warehouse, what happens? We do have a single schema and shared customer ID. Now just imagine we have stored all these things in the data warehouse. Now just imagine the customer has asked again this same kind of question: who bought product X and opened a support ticket within 20 days? So now we have stored everything in the data warehouse. Using a single SQL query, we could have able to get the data which is customer requested for. If you see, we'll be selecting the customers and everything from the orders table. So we only need these two tables here, orders and the gender tickets. So if you see, we just took the orders tables and joined it to the tickets table, and on the specific customer ID, where product equals to product X, and ticket date is less than the 30 days, or order date is less than the 30 days. So this is a simple SQL query. Using the simple query, we could have able to get the data what the customer is requested for. So this is the problem with the multi-source DBs, and this problem is being solved by the data warehouse. See, now the third problem is the historical data problem. I'll just explain you what exactly it means. So basically, production DB is take care of, only cares about what exactly happening right now. So just take an example of orders. So this is how the production data mindset be like. If the order is in pending state, shipped state, or delivered state, that is what exactly the production DB take cares about. Just imagine we have updated the anything, maybe in any order or any row, it obviously overrides the old state and it doesn't have the history of the previous record. Same way, if we have deleted anything, it's gone forever, we don't have any history data. Now just imagine the customer asks question something like, what is the churn 18 months ago? Obviously this only keeps the current records and totally overrides the existing records, so it doesn't have a clear answer. This is the problem with the production device. Now just coming back to the warehouse mindset, so it doesn't, it will just append to the existing DBs. So if you see here, it's every day it adds a new row, it has a full history so that we can query anytime any day we want. So this is a big advantage of the warehouse. So database, production database will override the data and this will append the data if you see the example here. So what is the advantage of this? See, usually the main thing, businesses mostly live in the past. So most of the customers will be asking questions something like, what's happened in the past? Like what QOQ revenue growth, what's the churn 18 months ago versus today, for example, what is the seasonality over last 3 years? So they want the history data for their internal purposes or whatever. So the reason why we need to use warehouse is it has the timeline. It stores all the timeline here. So if you see, there are three problems here with the production DB. One is performance, other is fragmentation because the data lives in different places. Another is we don't have any history. Production DB take cares about only present. So all these problems are being solved by the data warehouse. For example, data warehouses are BigQuery, Snowflake, Redshift. All three are the data warehouse. So if you see, I've mentioned 3 points here. One is it has a separate workload, and it has the unified schema, and it has history, so that this will be very helpful for the business related purposes. When the customer asks and comes up with any question, it has the overall history, and it has a unified schema, so we can use joins and answer the customer in just using a simple SQL query. So this is about our first concept of the real problem and the solution of why we need to use the data warehouse. Okay, guys, till now we have seen the real problem of why the production DB doesn't work, and why we are going to go with the warehouse. Now in this next steps, we'll be seeing what exactly is the data warehouse. In this, we'll be discussing first about the OLTP versus OLAP in detail, the difference and everything. Then we will come to the row-oriented storage versus column-oriented storage. This is like most important topic in the overall video, and we'll see why exactly this columnar storage, makes the analytics types of queries very faster. Let's go to the first topic, that is OLTP versus OLAP. Yeah, if you see here, the abbreviation is very straightforward: online transactional processing, online analytical processing. So here the term transactional exactly means, some kind of operations, for example creating or updating or deleting, which 99% affects only one row. For example, see our OLTP applications like PostgreSQL, MySQL. For example, just taking this example, get this one user, and this will only insert one order or one row. If you just take the update, it will only update one row. So yes, there are like only one row. It will usually take very milliseconds of time to perform the operation. So that's what here I mentioned. It's very narrow and precise queries because just updating or creating or deleting a single row, and minimal records are touched. In this case, if you see only one record is being touched, like getting the user or inserting a user or updating the payment status, everything, one single row is touched, or minimal number of rows are touched here. And we can handle like 1,000 number of requests per second in this case of request. And obviously there will be fast rates and the strong consistency here. This OLTP is explicitly optimized for single row reads, as I mentioned just now. And usually if we have single row reads, we can write thousands of records per second. So obviously there will be the fast rates, and there will be no lost updates here. This is all about the basic meaning and use of the OLTP. Now let's come to the OLAP, online analytical processing. As a term here itself says analytical, so this is mostly used by the business people to know the latest analytics and everything. What analytics requires? So data the warehouse. See, if you see this application database, everything requires this OLTP, and here for OLAP data warehouses are very mandatory. I'll show you why. Now just imagine the customer has, or the businessman has asked something like revenue by category in the last 24 months. Now what exactly happens? So if you use this OLTP, it's a transactional based processing, right? So usually it is not fit for analytical. If you see here, we need to query the last 24 months whole data. It might be in n number of million records, but here this OLTP is exactly best for single row reads, but here it's like millions of records reads. So that's the reason OLAP, it has wide and aggregate queries, like more complex queries it can be handled, and millions of records will be scanned. Because it's a warehouse, it stores the overall history of the specific use case or the specific record or specific whole thing. And so we can able to scan millions of rows. And yes, it is infrequent because we have the lot of history, but yeah, it's also expensive here. And if the customer asks any such kind of questions here, maybe revenue of last 24 months or what kind of questions and everything, we can just complete it just using a single SQL query. So when it comes to the reason of what it is exactly optimized for, full table scans. As I mentioned previously, there are many reasons why we came to warehouse. So all the data will be present in the same bucket, or same source. There might be different sources coming from the different ways, but all these things are stored in the data warehouse. So full table scans are easily possible here, and lot of aggregations are possible. And it's basically column reads. I will come to these column reads and row level reads in the next section, but let's keep this thing in the mind. So as I mentioned, data warehouse is usually a OLAP systems. See, the one of the main trade-off between OLTP and OLAP is if the DB is OLAP optimized, or if the DB is optimized for OLTP, it will obviously be bad for the OLAP. and it would be reverse also. If the DB is best optimized for OLAP, it will be bad for the OLTP. So the whole concept, the main reason, if you see the title, two different shapes of work. So it is designed for different work. So this is designed for one type of work and this is designed for other type of work. You cannot use both in a single DB. So here I mentioned the basic difference between the OLTP and the OLAP. You can just go through it. It's very and that's what exactly we discussed till now. If you see, it its query shape is like one row. It's millions of rows, and it's a row oriented. It's a columnar oriented. Obviously, it's latency. It's low latency, and it has like coming to the next topic is it's about a row oriented versus columnar oriented. This is like most of the important concept on this overall video. I'll just say you why. See, there are two ways of storing the data. One is row oriented, other is columnar oriented. So these Postgres and MySQL, store the data in the row format, and these BigQuery and Snowflake and everything store the data in the columnar format. Let's take an example. So row oriented is nothing like a spreadsheet. Okay. For example, just take we have these columns: ID, name, email, country, sign up, and revenue. So for example, we got a query something like this. Okay, select star where ID equals to 7. So it just reads one block. See, if you, it will just go through one by one, and it will just find out if the ID is 7. Then it will return this row. This is very straightforward. But just imagine the case where customer or query is something like sum of revenue, just sum of revenue. Okay, now what it does, it will read all these column names on all these rows. Assume there are like 50 million rows. It will go through all the columns and all the rows, everything, and then it will get remove all these unnecessary columns. It will only take the revenue column, and then it will aggregate or sum it. If you see, it will read each and every row, pulls. These 5 columns are literally unnecessary, but even though it will pull because it's row based. This is one of the big drawback of this row oriented. Now comes the columnar. So these BigQuery, Snowflake, Redshift all use the columnar based storage. So as the term says, it instead of storing row wise, it stores the column wise. Each column is totally independent of each other. For example, see, IDs and everything stored in this column, countries and everything stored in this column, revenues are everything stored in separate columns. So now when the customer or query is something like sum of revenue, it don't need to read all these columns. It will only come to this column. It will only take this column and it will get the sum of all these. It is very straightforward. It's only reads only one column here. And when it comes to input output, for example, just take this example. For this input output will be like, reading all these columns here. But here input output obviously will be dropping because we are not even touching all these columns. We are only taking care of one column. So that's what I'm saying. Like it's just a number, but most of the unused columns will be never touched in the columnar based storage. Now there are three big advantages of using the columnar. So first is compression. If you just take this country here, as it is stored in the columnar format, if we have similar names or similar values like India, US, these are the similar country codes or similar terms, right? If you have similar terms as it is the columnar based, it will compress into like as is based, so that the size is like almost nothing. See, the raw storage, this raw oriented cannot do this because it's a mix and combination of different data types and values. If you see, it has the ID might have the data type integer, name is string, email will be string, country will be some code or anything, and there will be the revenue will be the maybe integer or float. See, it's a mix of different values. For example, when it comes to columnar, it's unique. Revenue is every time float or integer, country will be the string, this way. So that's the reason compression is the one of the biggest advantage in the columnar storage. The other advantage in the columnar storage is the parallel reads. So here we cannot do the parallel reads because all we need to scan all the column names here. But when it comes to columnar, each column is independent to other columns. So for example, there are like 2 to 3 workers, and one worker can go through the ID, other worker can go through the country, other worker can go through the revenue independently. This is the one of the other advantage. See, one of the main reason why viruses finish in seconds. If you take any query, assume the query contains the data to be read only in the name column, it won't go through the other columns. It will just ignore everything and it will only focus on the name column. This is the one of the main reason why warehouses queries is very fast, even if it is analytical and even if it is scanning like huge number of million records. This is about the row oriented versus columnar oriented. Okay, now let's take an example and we'll understand this concept in very detail. Just imagine we have 100 million rows and 20 columns, and we have a query something like select country and sum of revenue from orders table will group by country. So in the row storage like Postgres or MySQL, we need to read all the 100 millions row of the disk because we are need the sum of revenue here. So we need to go through each and every column and all the 100 millions rows here. This is the one biggest disadvantage. And as I mentioned earlier, all the 20 columns per row. For example, just imagine country is present in this column and revenue is present in this column. So to get these two columns, it needs to go through all these 20 columns to get the country and the revenue details. And once we got all this data, now we don't need all remaining columns, right? So it will remove all the remaining columns. This is one of the unnecessary operation in the row storage. So once it removes, we do have only have the country and the revenue, right? Now it will get the sum of all the revenues and by the it will group by country. The aggregation will happen, then it will return the output. So if you see the amount or charge paid to complete this query is for 20 columns, it only uses two row. So if you see the paid input output for 20 columns is to only use two columns. The meaning is so we only need two columns on here, but we paid the amount or charge for all the 20 columns. This is like total unnecessary thing. But the best way of the columnar storage here, taking the example of BigQuery or Snowflake or Redshift is, now just imagine we have like n number of column names. We only consider about the country and the revenue. The columnar storage will only read the countries column and the revenues column, and all the remaining 18 columns are even never touched. They don't even care about those remaining columns. And all these columns are also be compressed, so there will be fewer bytes which are read. Okay, so and also there will be parallel workers which reading these separate individual columns simultaneously. So if you see paid input output here is like it literally 1 by 10th of the row storage because we didn't even touch the all the columns. We only take care about these two columns, and also both are processed parallelly. Like this is one of the big advantage. And also compression is the one more thing. This data is already compressed as it's independent to each other. So yeah, here if the three compounding advantages, and here is one is less data read. So here we need to read the all the two rows, and here we just need to read the two columns. And the second is better compression. As we have the similar values together with the similar data types and everything, the compression would be very much better here. And as one column is independent to other columns, these can perform parallel execution. Actually, BigQuery, Snowflake, Redshift, Databricks, all these latest trending things whichever you listen are all the Columnar latest storage models. Okay guys, now we will see how exactly this data warehouse works. So in this we will be mainly discussing about the main difference between the ETL versus ELT. Once you understood this, the main question and the main concept here is where exactly the transformation happened. This is the main difference between these two. Okay, now first let's start with the ETL. So as the abbreviation says, it's extract, transform, unload. See, the first thing is the source. If you see anywhere in this world, in each and every second, the data is coming from everywhere. Right now, the video which you guys are watching is the source data for the YouTube. So the source data is coming from lot more places. For example, just take the Stripe for the payments, APIs, etc., etc., everything. So once we have the source data, the first step is to extract the data, meaning pull the data. So we will be first pulling this data, and this step is called the extract. Once we extracted the data from the source, then we will be transforming the data. Here we might be having a pipeline or a best just in Python script or whatever, but the transformation part here usually does the cleaning or reshaping or removing null values. Anything it comes under the transformation, everything will be doing in this part. And then once the transformation is done properly, we will be then loading the data into the warehouse. So this is the simple steps of the ETL. And the main question here, where does the transformation happen? This transformation happens in the middle of this pipeline. If you see these three whole steps, the transformation happening is this middle. Now when it comes to the ELT, extract, first load and then transform. If you see here, first transformation and then load, here the process is reverse. Now again we have the source data coming from a lot more places. First we'll be extracting the data. The step is same as the previous one. We'll just pull the data from the source. Now, instead of directly transforming, what we will doing, we will be directly storing this extracted raw data into the warehouse so directly. So once we have this raw data directly into the warehouse, then using the data from the warehouse, we will be performing the transformation here. Like we'll be doing some SQL operations and etc. Directly into the data warehouse. Here, transformation exactly happens inside the warehouse, not exactly in the middle of this section. It happens at the end exactly once the data is queried. Now, if you see in the ETL, the warehouses sees only the processed data. If you see, we pull the data, we clean the data, and we store in the data warehouse. Now, this warehouse doesn't have any idea, doesn't know what exactly is the source and the raw data. It only sees the clean and reshaped data. But when it comes to the ELT, it actually sees the raw data because as soon as we extracted the data, we directly stored into the warehouse. The raw data is stored in the warehouse. So this warehouse sees the raw data plus the transform data both. If you see, the raw data is stored into the warehouse and transform data is also stored into the warehouse. So this is one of the main difference between the ETL and the ELT. Now, if you see in this generation or from past few years, this ELT is winning a lot. Let me show you the reason why. So if you see here, the reason why ELT1 is, so previously the storage and compute cost was very expensive. For example, we'll be getting the lot of data with a lot more places from the lot of sources, but the place where we store and the cost of the storage and the cost of the querying is very huge. So that's the reason people what they did beginning itself, once they extract the data, they'll storing the transform data into the warehouse, so the storage and the compute cost will reduce for them. But recent years and recent generation, what exactly happening, this storage part is very cheap and compute is also very powerful. If you take bigquery, the storage cost is very cheap and the way it queries is very fast. So because of these main reasons, now most of them are shifting to ELT. If you see the previously, transformation was, previously they used to directly store the transformation. Previously they used to store directly transform data because the warehouse storage or compute was very expensive. This is one of the main reason why ELT won here. And what none of the most superpower of the ELT is, we have the access of the both raw data and the clean data. And one of the big advantage of it is, just imagine we found the bug in the transformation here. What we can do, we can directly fix this SQL query and we can just get the data. Just imagine in this case in the ETL, if we found the bug in the warehouse, so what we need to, this warehouse doesn't even have idea about this raw data. So what needs to happen here, first we need to transform this whole data again and then we need to load the data into the warehouse and we need to show it to the business. So the transformation part happens here, right? So whatever issue comes in the warehouse, first fix needs to be made here. So these steps need to be rerun again if any bugs come up in this warehouse. But in this case, here in the ELT, if the issue or bug come up in this warehouse, we don't need to run the whole thing because this has the access to the raw data directly. We can do the transformation fixes, SQL fixes, everything here itself, and then show it to the customer or the business purpose or where they want. So this is what I'm exactly mentioned here. So ETL never store the raw data here. So it's like gone forever. But in the ELT, we can just fix the SQL query and rerun as the raw data is always sitting there. Okay, now the next topic is the three warehouse layers. We have the three warehouse layers here. One is raw, staging, and mods. One of the main question is why we need the three layers, but we will come to this part later. To answer this, first we need to understand what are those three layers and what exactly the use case of the each. Now let's start from the here. It should be in the reverse order first, so that will be coming from below. First is raw data. This is like a landing zone. This is where all the source data comes. Here we'll be having the nulls, duplicates. The data never deletes here because we don't do any kind of operation here. We will be just storing the raw data as it is here. It's like a ground truth of the data. If something happens or something breaks here anywhere, we can directly restart it from here. That's the reason we have this raw staging layer here. Sorry, raw layer here. So it has the source truth of the data. Now next comes the staging data. This is the place where we do all kind of transformation and we store the clean data. If you see here, it is still the raw data but trustworthy. The meaning here we will be removing all the duplicates, all the non-regular types, and we'll be renaming the columns and have the meaningful naming convention and anything handling null values. All these kind of transformation will be happening in this staging. So all this kind of transformed data will be stored in the staging layer. If you see here, we don't have any business logic. It is just a place where we store the clean data. And finally it comes the Marts. It's like an place where the business logic exactly lives. For example, if you want the any query, for example, if you take the customer ask the query to get the latest trends of the last year or whatsoever, so the SQL or the SQL models or whatever will directly talk with this layer. It doesn't either talk with these two layer, it only talks with this layer. And the dashboards or whatever will be pointing here only. All these dashboards and everything we built will be querying the data from this layer only. Now the question is, who uses each layer? See, these raw data or this staging layer, this layer is mostly used by the data engineers, because this is where we guys, data engineer guys, take this data and play around. Now comes the staging. Here we data engineers also involved here when it comes to transformation and everything, and also dbt or SQL people who usually get the data from here and the query the data. And the Marts, mostly the business analytics people. These are the people who directly work in this layer. And one main condition here is we never point the tabular or any analytical tool at the raw tables. They will be only working in the Marts. Now coming back to our main question, why we need the three layers and not one single table? So just imagine, for example, if the business logic gone wrong here. For example, if the business logic has gone wrong, so we can just rerun the Marts SQL instead of without even touching the staging or the raw. This is under, just take one more example. If the cleaning logic has gone wrong, we can just rerun this staging layer instead of touching the source system. We don't need to touch here. Anyways, we have the data here. We don't need to do anything here. If this has some issue or anything, we can just directly clean the data, maybe update the Python logic or whatever. You can just perform the operations here even of touching the here. Same way as I mentioned earlier, if something business logic gone wrong here, we can simply fix the SQL query without even touching these two layers. This is the one of the main reason we maintain three layers and not a single one clean table. Okay, now we will see the full architecture of this whole thing from source to business. See, each and every data role somewhere fits in this overall flow. And this will answer the most important question of what exactly data engineer's job does. Okay, we'll start from source. This is actually already discussed. I'll just go through, very high level. See, we have the source systems as we discussed earlier. We don't do anything here. We don't even control this part. So once we have the source data, it will be coming to the pipelines, or we will be doing the ETL or ELT pipelines here. Here, the most of the main data engineer job comes, like creating the Airflow DAGs or composers, or creating the data for pipelines, or using some Python scripts or scheduler. Everything we'll be building some pipelines where we perform these kind of ETL operations. So this is main part of the data engineer job. And once the loading the ETL jobs or ELT jobs are done, the data is usually stored in the data warehouse. As I discussed earlier, we have three staging layers. One is raw, staging, and mods. So once the data is now in the warehouse, now the business intelligence layer comes. Using this all these tools, we'll be building the dashboard. So does this doesn't usually come under the data engineer part. I'll just explain you why. But yeah, using this Looker, Tableau, Power BI, each and everything, using these tools, the business intelligence guys build the dashboard. And once we have this dashboard, whenever the business user asks a question in simple English, the answer will be getting in the seconds in the dashboard. If you see now, the main part is this source is, we don't even care about the source because we don't even control it. Especially this part is the place where the data engineer guys own the pipeline place data warehouse layers. This is the place where exactly these data engineer guys works. And once this is done, this is again not our cup of tea. Mostly business intelligence guys or business users will take care of this part. The main promise we give to the business guys or the customers is, just imagine whenever business intelligence queries the mods, this will query the mods, and warehouses, these warehouses will answer the questions within the seconds. But which usually takes an hours, when which usually engineers take hours to answer this question. This whole pipeline, this whole thing makes the business users questions answers within a seconds. Now we'll just see in very high level which are the tools we'll be touching in this overall flow. For ingesting, we'll be using these tools, mostly custom Python or Airbit or few other tools which we'll be using for the data ingestion. And for orchestration purposes, mostly the top number one is the Airflow, and for GCP it's Cloud Composer. And for transforming, we'll be having the data flow pipelines or DB2 tools or SQL and few other things. When it comes to storage, these are the top: BigQuery, Snowflake, Redshift. These are the top storage layers or storage tools or whatever. And for serving, it's obviously Looker, Power BI, Tableau, etc. These are the like nothing but the dashboards. So this is what exactly the end-to-end full architecture is, from the source to business. Cool. Now we have seen what exactly the ETL and the ELT difference and all about these things. The next steps are actually the BigQuery specification and the common mistakes. As these two are obviously dependent on it, but I'm planning to create a separate video on it. If you guys tell me in the comment section if you really want in detail concept about this BigQuery specifications, like how exactly the BigQuery stores the data and what is the difference between compute versus storage engine in this BigQuery, and detailed about partition and the partition pruning and about the clustering, and this all comes under the BigQuery. So please let me know in the comment section if you really need a separate video on this BigQuery specification. I am also planning to include the BigQuery costs and everything along with these concepts. And this is like very high level. What are the main common mistakes which we do in the data warehouse concepts? For example, like using a data warehouse as a point lookups. This is not the right case. As I mentioned, lookup should be only in the Marts, not in the different layers. For example, we should be doing data lookup should be only in the Marts, but not in the raw layer or the staging layer. And data here warehouse is the data where lake, this is also not the same thing. It has a huge difference, and obviously I'll create a separate video on this if you guys are interested. IST. So, and there are few other common mistakes. You guys also let me know if you want a separate video on creating a separate video explaining all these kind of mistakes, and just let me know in the comment section. Okay, that's it guys. So if you really like this video, please let me know in the comment section and hit a like button, and don't forget to subscribe to my YouTube channel guys. Thank you.